Good day everybody, my name is Jaouhar Fattahi. I am from Laval University. Today I am going to present our paper titled Case Semantics for Security Policy Enforcement on Android Applications with Practical Cases. Android applications represent a double-edged sword for the Android system. They contributed to position Android among the most used mobile operating systems given their variety, but at the same time, they helped malware creators infect its devices. According to the McAfee report, illegitimate applications are the most active mobile threat category, generating nearly half of all malicious telemetry, with a 30% increase over 2018. These applications can be downloaded from sources other than the official ones, like Google Play Store, without being subject to a rigorous review process. However, to address this, Android security adopted solutions to protect its users are not sufficient. When installing an Android application, the user has two choices. Either he accepts all the permissions requested by the application or none of them. To make this decision, the user has no idea if the application has something to do with his private data. Indeed, Android users are exposed to attacks targeting the Android system through malicious applications. To address such a problem, solutions for enforcing the security of Android apps are highly needed. However, without a formal foundation, nothing is guaranteed. Formal methods are based on a mathematical logic that allows to specify and verify a given system rigorously and guarantees the correction and the proof of results, which is not the case of test-based approaches. Formal methods combined to the aspect-oriented paradigm is the perfect combination to automatically incorporate aspects such as the security aspect into a system while producing systems that meet their specifications. In previous work, we put forward an approach for security policy enforcement on Android applications. We defined an enforcement operator that takes as input an Android application, in particular a formal specification for the smiley code P generated by reverse engineering, and a security policy specified as an Ltl formula phi, and generated a new version of the smiley program P' that respects the policy. Smiley is a humor-readable representation of the Dovec bytecode in the classes.dex file, generated from reverse engineering Android applications. We use the backsmiley disassembler included in Tool to obtain Smiley and the rest of files in a readable representation. The approach proposed in the previous paper consists of 5 main steps. The first step is a formal specification of the security policy. For that, we use the LTL logic to describe the security policy. The second step is the formalization of Smiley. We use the language definitional environment K-framework to define a formal and executable semantics for Smiley that we called K-smiley. The third step is to transform the Ltl formula into a K-smiley program. For that, we simplified its syntactical form to bring it closer to the syntax of Smiley. Then, we transformed it by adding some control actions to be able to monitor the program. The step number 4 consists in transforming the Smiley program so it includes the complementary part of synchronization actions added to the policy. And finally, we run the two programs in parallel so they can synchronize, and we obtained a formula that drives the program as wanted. The solution is effective since it is formal and can be proven correct. Nevertheless, it is too theoretical and needs automated tools to show its feasibility and efficacy. As an improvement, our goal is that all steps from formalization to enforcement will be performed using automated tools. For this, we choose the K framework. It is a semantics engineering tool that offers a plethora of tools such as an interpreter, a compiler, a model checker. These tools allow to produce an executable semantics that can be tested against sample programs and can be verified and compiled, so any possible error or details omission can be detected. The K framework takes as inputs a security policy, a Smiley program, and a manifest XML file. It defines a formal language for both inputs. It also enforces the policy on the program and produces a secure program that behaves according to the policy. As a first step, we define the K syntax of the Ltl formula, so it can be the Boolean constants true or false, a termination action 1, a sequential composition of two formulas with dot, a disjunction of two formulas, and an iteration with star. Then we define the K Smiley with a syntax and rewriting rules. So an Android application program consists of a list of Smiley files and a manifest file. A Smiley file is composed of a class. A class is composed of a list of fields and methods. A method body consists of a list of directives and instructions. Instructions include those related to multithreading, method invocations, subroutine instructions like move, and constant instructions. Now, to enforce the Ltl formula on the K Smiley program, we define a K syntax. So, in line 7, the enforcement syntax consists of a K Smiley program modulo a set of actions to be controlled, enforced by an Ltl formula. After defining the syntax, we define the configuration. It consists of a set of labeled cells, a program cell containing the program to be enforced, and the formula. and an enforced program cell containing the new program after applying an enforcement policy. After defining the program syntax and the configuration, the next step is to define the rewriting rules. So, all semantics rules for the program and the formula transformation, the formula integration in the program, and the enforcement are defined using K. The rule Ltl to smiley allows to transform an Ltl formula into a smiley program. For example, the Formula 1 is transformed into its equivalent instruction in smiley NOP, which means no operation. The second rule transforms the GET action by adding control actions send and receive before and after. The rule enforcement transforms the program by adding synchronization actions receive and send before and after each action to be controlled. Let's consider the example in listing 3. A k-smiley program modulo a set of actions to be controlled, new instance, go to, invoke virtual, and invoke static, the all to be enforced by the Ltl formula, including the iteration operator star. Then we use the interpreter offered by K and obtain the rewritten program in listing 4. As you can see in blue, all control actions are added in their appropriate positions in the program. In green, the policy is as well added as a k-smiley method fee. In red, the program and the policy threads are launched in parallel. So, to sum up, we use the K framework as an environment to harbor our approach that takes a formal specification of an Android application as well as a security policy as inputs. Then it applies a sequence of modifications and adjustments and generates a new version of the program that achieves the policy goals. From the introduced formula, and in an elegant way, the semantics allows to identify automatically the relevant points in the code in which security controls should be inserted. Thank you very much.